Okay, good morning, ladies and gentlemen. Um, we are about 6 minutes early. In the meantime, if you could just indicate in the chat whether or not you can see my screen okay and whether or not you can hear me okay. Again, good morning, ladies and gentlemen. We're about 5 minutes early. Um, I am now currently unsure whether or not you can hear me okay and whether you can see my screen okay. If someone could just indicate in the chat that everything is working fine. Okay, perfect. Thank you. Okay, thank you. That looks like everything looks fine. Reason why I'm asking is I'm using a little bit of a different setup this morning because of the load shedding. Um, so I just wanted to make sure about that. Okay, so with that said, we are about 4 minutes early. So the lecture will start at 9:30. So in about 4 minutes time. So please bear with us. Okay, good morning, ladies and gentlemen. It is 9:30 on my watch. So let us start our lecture for WTW 124 this morning. So I am currently on a little bit of a different setup than I am used to, so there might be some hiccups, hopefully not. That is because of the load shedding. And let me also add, there is a remote chance that at 10, when the power comes back on, that I might lose network connectivity. So I will then try to come back, but it is also not a train wreck if the network doesn't come back. Point is, we've done everything that we possibly can to limit the disruption from load shedding. Okay, so let us start with today's lecture. So let me just make sure my audio appears to be working and my stream looks to be healthy. Okay, good. So everything appears to be fine. Okay, so where did we end at our last lecture? At our last lecture, we discussed a couple of theorems regarding lines and planes. So for example, if two lines intersect in a unique point, then there is a unique plane containing those two lines. We didn't prove that, but we, if I remember correctly, we did discuss an example. And then also we discussed a theorem that says discussed parallel lines and planes. So for example, if we have two parallel lines which are different, it's important that they are different. If they are different, then there exists a unique plane containing these two parallel lines. And that theorem also had a second statement. So for example, if we have two lines in the same plane, if they do not intersect, then they must be parallel. So if we restrict two lines in the same plane, then if they do not intersect, then they must be parallel. And that is all fairly intuitive. There is not, let's say, the intuition behind that is, since we're working in 3 dimensions, it's fairly easy to visualize what is going on. Okay, there's one thing that we didn't do, one very obvious thing that we did not discuss yet about planes, and that is we did not discuss how to determine the intersection of planes, or the intersection of lines and planes. The reason for that is, well, let's say we could do that. So, we have all the tools that that we need to do that. To be precise, we have now described parametric equations for lines and planes, and with that we can determine, for example, all the points of intersection of a line and a plane and two planes. However, using the parametric equations for lines and planes, that becomes rather tedious because there is what I will call a proliferation of parameters. So for that reason, we will discuss let's say a different method which is more efficient in determining the intersection of lines and planes. So that is where we are heading towards. So the words that we are, or let's say the term that we are heading towards is what is called the Cartesian equation of planes. But before we get there, we first need a couple of let's say, some technical theory before we can get there. So today what we will introduce is what is called the cross product of vectors. So the cross product. Okay. And let us take a look at the definition of the cross product. This is definition 1.7.1. So let U be the vector U1, U2, U3, and let V be the vector V1, V2, V3. Okay, and then we define the cross product. So we define the cross product of U and V as follows. So the cross product of U with V, that is a vector, and we define it as follows. So, and this might look a little bit strange to you. Why is it that we define it in this way? It is. That question doesn't really have let's say, an easy answer. So we will not go into why exactly it is defined in this way. A little bit later on, we will discuss, let's say, the geometric interpretation, which somewhat motivates why it is defined in this way. But it is going to look a little bit strange for now. So this is the cross product of U and V. First of all, it is a vector with three components. So let's write out what the components of this vector is. So that is U2 times V3 minus U3 V2. So there we have the first component, and just because I don't have enough space, I'm going to write in this in the next line. The second component is U3 V1 minus U1 V3. Let me make that 3 a little bit better. 3. That is the second component. And the third component is U1 V2 minus U2 V1. And again, let me emphasize, this is a vector. This is a vector in R3. Vector. Okay, so there we have defined the cross product. And like I said, if we look at the components of this vector, it appears to be a little bit strange. Why is it that we are defining it that way? We will discuss that a little bit later in the lecture. Okay. So how are we going to remember how to work out cross products if it looks so strange? So let us discuss a mnemonic for working out the cross product. So U cross V again. So the easiest way of remembering how to work out the cross product is as follows. So what we do is we write out our vectors U with its components U1, U2, and U3, like so, and V1, V2, and V3, like so. And it's very important, the first vector should be at the top. So if we have a U cross with V, then the U should be at the top. So U cross V, the U should be at the top, and then the V at the bottom. Okay, and so now, how do we remember how to work out the cross product? So what we do is the following. So we need 3 components. I'm going to I'm going to write them below each other because I don't have a lot of space. And the first thing that you do in the middle component, what we need is a minus. So I'm going to put that in red. So remember, put a minus in the middle component. Then what do we do? Let's show how to work out each component of the cross product. So to get the first component, what do we do? Well, we cover up the first two components, and we look at what is not covered up. So, and then what do? We say u2 v3, so these two vectors minus, or the product of these two components minus the product of those two components. So u2 v3 minus u3 v2. Okay, so that gives us our first component. Okay, and now to get the second component, what do is we cover up with our hand or with our finger the middle two components, and we look crosswise like that. So that is u1 v3 minus u3 v1. Okay, and very important, don't forget your minus sign here. The signs of the components must alternate. So my suggestion would be at the very beginning of your calculation, always remember to put your minus sign in the middle component. Okay, so now we have the middle component, and now we can do the last one. So let us do that. And what we do for the last one is we cover up with our hand those last two components, and we multiply crosswise like that. So the last component, u1 v2 minus u2 v1. And there we have our mnemonic for working out the cross product of two vectors. Okay, let me just take a look at the chat if there are any questions so far, and if the stream is appears to be working okay. Everything appears to be healthy. And in the chat, okay, it does not appear that there is anything in the chat that we have to address so far. Okay, very important, let me reiterate. The dot product of two vectors is a scalar. The cross product of two vectors is a vector. Do not ever mix these two up. So make sure that you understand the definitions of the dot product and the cross product. Okay, let's take a look at a few examples. So what we're going to do now is we're just going to compute the cross product of a couple of vectors. So example, let u be the vector 1 minus 2 1, v, let that be the vector 3 1 minus 1, and w, let that be the vector 2 minus 4 2. Okay, and let us compute u cross v. Actually, let me write it a little bit further down. U cross v. So remember, what do? We take our vectors u, and we write u at the top because u is the first component or the first parameter in our cross product. So 1 minus 2, 1. And v is 3, 1 minus 1. Okay. So let us work out what the cross product is. So remember that is, we've got 3 components, and remember the middle one, we always need to have a minus. So immediately put a minus in there, and I'm going to put these 3 vertically below each other just because I don't have enough space. Okay, and don't forget your minus in the middle. Oops. Okay, so now let's work out our first component. So what do is we cover up our first first 2 components, and we work out crosswise like so. So that is minus 2 times minus 1, which is 2, and minus 1, which is 1. Or let me write that out. That is minus 2 multiplied with minus 1, minus 1 multiplied with 1. Okay, so that is our first component. Let's work out our second component. That is going to be 1 multiplied with minus 1, minus 1 multiplied with 3. That is our second component. Third component is, we cover up our third components. That is going to be 1 minus 6, which is plus 6. And let's work out what that is. That is 1, 4, 7. So here we've got 2 minus 1, which is 1. Second component is minus 1 minus 3 multiplied with minus 1, which is plus 4, and 7. 1 plus 6 is 7. So here we have the cross product of u and v. Okay. Now there's something we should notice. Let's take the cross products of v with u, and let's see what that is. So let me write out v. So v is, what is that? 3, 1 minus 1, and u is 1 minus 2, 1. And let's work out v cross with u. So that is a vector. I'm going to write it vertically just because I don't have enough space. Remember, in the middle, for the middle component, we always need to have a minus. So let's immediately put our minus in there. Don't forget your minus. Let's work out the first component. So we cover up the first components. We do crosswise. That is 1 minus 2. So we're going to get minus 1. Actually, if we are good at our mental arithmetic, then we're not going to need so much space. So let's do it this way. Okay, so we've got our first component, which is minus 1. Let's do our second component, cover up the middle. So that is going to be 3 minus 1, which is plus 1, which is 4. But don't forget your minus there. So always remember to put your minus in the middle component. Okay, so now we've done our middle component, and let's do our final component. Okay, cover up our last 2 components, and that is going to be, what is that going to be? That is minus 6 minus 1, which is minus 7. So that is equal to minus 1, minus 4, minus 7. Okay, and what we should notice here is u cross with v is 1, 4, 7, and v cross with u is minus 1, minus 4, minus 7. And the thing that we should notice here is that u cross with v is not equal in general to v cross with u. So the cross product is not commutative. We cannot swap the first and the second inputs in the cross product. U cross v is not the same as v cross u. Okay, let me take a look at the chat if there is anything that I need to address. Let's take a look. There is someone saying the connection is bad. Everything appears to be okay on my side. So it appears that it is on your side. Remember that the stream will always be recorded and you can always play it back if you need to. There is a question by James Tibshreni. Is it possible to get the cross product of more than two vectors? Well, yes. So if we think about it, we can do something like u cross with, let's say, v cross with w. 3 is not a w. So remember here, this is now a vector, and well, the cross product on both sides, the cross product, we need to put in another vector. So this is perfectly valid. So you can work out the cross product of more than two vectors. However, that is different. For example, u dot with w, that is not defined because that is a scalar. So u dot with u dot with w is a scalar. So we cannot take the cross product in that way. So let me erase that immediately. Okay. Let's do one more. So let's take a look at u cross with w. So let's write out u, 1 minus 2, 1. And let us write out w, 2 minus 4, 2. And let us work out this cross product. So remember, always in the middle component you need your minus. Don't forget your minus there. And let's see what we get. So, oops, that was the wrong button. What was that first component? 1. Okay, first component, cover up the first components. That is going to be multiply crosswise. That is minus 4 minus minus 4, which is plus 4. So minus 4 plus 4 is 0. So now we have our first component. Second component, cover up the middle components. That is 2 minus 2, which is also 0. Okay, and let's cover up the third components. That is going to be minus 4 minus minus 4, which is also 0. Okay, so there we have our cross product, and we see here this particular cross product is the 0 vector. Okay, and do we perhaps see something that is common to these two vectors, or is there a relationship between these two vectors? What we should see is if we take u and we multiply with the scalar 2, then we will get w. So that appears to be something to keep in mind. If we have scalar multiples, then it or if one vector is a scalar multiple of the other vector, then we tend to get a 0. Okay, let me take a look at the chat if there's anything that I should address. There is a comment or question by Mr. or Ms. Quella. Will the cross product always have the same magnitude and just different signs when you swap the vectors around? Yes. So that is actually a topic in the theorem that we will discuss now. The point is that if you u cross with v need not be equal to v cross with u, but if you work out the norms of u cross with v, that is going to be the same as v cross with u. And it is important to use the correct terminology. So since the cross product is a vector, we can talk about the norm of the vector. Okay. And also notice here is something different. So we can have two non-zero vectors give a 0 cross product. So it is that is important to notice. So that works differently from real numbers. Remember, if we look at the product of two real numbers, if the product is equal to 0, then one of the real numbers must be equal to 0. This is different. Here we've got two non-zero vectors whose cross product is 0. Okay. Let's take a look at theorem 1.7.4, which lists the properties of the cross product. So let u, v, and w be vectors in, that element is not very good, vectors in R3. Let alpha be a scalar. Then the cross product satisfies the following. So first of all, the cross product of u with v, that is not necessarily the same as the cross product with v with u. So v cross u is not necessarily the same as u cross v, but there is a relationship between these two. And what is the relationship? The relationship is that they point in exactly opposite directions. So u cross v is equal to minus v cross u. And this also shows that if you think about the properties of the norm, why the two norms of these two cross products will be the same. That is with if you take a scalar out of the norm, remember, then you get an absolute value. Here we've got absolute if we take the norm of these two vectors, we will get the absolute value of -1, which is just 1. So we can see that the norms will be the same. So secondly, the cross product distributes over addition. So v plus w. So if you take the cross product of u with v plus w, that is the same as taking the cross product of u with v and then adding cross product of u with w. Okay. And it also works the other way around. Number 3, if we've got u plus v cross with w, which is equal to, that is equal to u cross with w plus v cross with w. And why is this here? Well, it looks very similar to number 2, but since we know that the cross product is not commutative, we also need to check the other way around. So that is number 3. Number 4, scalar multiplication works as we expect. So alpha times u cross with v, that is equal to alpha times u cross with v. So we can take scalars out, and that is also equal to u cross with alpha v. So scalars or scalar multiplication works as we would expect for the cross product. And number 5, this one is fairly important. Oops, not u cross u. So u cross v, that is equal to the 0 vector, and that happens if and only if and only if u and v are scalar multiples of each other. Multiples of each other. Or in other words, there exists some beta scalar so that u is equal to beta times v. Okay, so here we have the properties of the cross product. Okay, let me take a look at the chat if there is anything that I need to address. Mr. Plint asks, is property 1 called anti-commutativity? I'm unsure. I think yes, and it kind of makes intuitive sense to call it anti-commutativity. It's not commutative, but when you commute u with v, then a minus comes out. So that's a good guess that this property will be called anti-commutativity. My suggestion would be to Google anti-commutativity and see if that is actually the case. There's another question by Mr. van Wyk. Is there a way of calculating the cross product in other dimensions? That is a difficult question. I'm going to say no. There are some special dimensions in which cross products work nicely. I believe in 7 dimensions or something. There is another version of the cross product, but I'm speaking under correction here. Okay, and I have just now lost power due to load shedding, so hopefully that answers your question, Mr. van Wyk. And now I just need to check that everything is still working fine. Okay, it appears that I did not lose network connectivity, and the stream still appears to be fine. Okay, so everything still appears to be fine. Okay, and the proof of this theorem, this is easy. So all that we do is we just use the definition of the cross product, And let me add here, it becomes rather tedious algebra. But it is not difficult. So all that it entails is a little bit of tedious high school algebra. So we will not discuss the proof there. Before we move on, let me just double check. Okay, everything appears to be working fine. Okay. Let us now take a look at the relationship between the dot product and the cross product. And this is the topic of theorem number 1.7.6. So let U and V be vectors in R3. Then the following holds. So if we take the cross product of U with V, so remember that is a vector, so it's perfectly legitimate to then take the dot product with U. And what we will get is that that is actually equal to 0. And similarly, if we take the dot product with V, with the cross product of U cross with V, that will also be equal to 0. Okay, so that is theorem 1.7.6. Again, the proof is easy. All that it is a little bit of tedious algebra. So we will not discuss the proof. What we will discuss is what is the interpretation of this. So notice here, there's no restriction on V and U. So V and U, they don't need to be 0. They don't need to be the 0 vector. So what is the interpretation here? Remember, when we discussed the magnitude of angles formed in space, there was a dot product involved there. And we also discussed how if the dot product of two vectors, or let's say two direction vectors of two rays, is 0, then the magnitude of the angle is pi over 2, or in other words, is a right angle. So what this is saying is that the cross product of U with V is always at right angles to U and V. So, for example, if we have a vector U like that, and a vector V like that, if we take the cross product of U with V, then what we get is something like this. So U cross with V, that is going to be at right angles to U, and will also be at right angles to V. That is what this theorem is telling us. So for example, if we are looking at the ray, let's say this blue ray with direction vector V, and we ask what is the magnitude of the angle with that red ray, if we work out the magnitude of this angle, what we will get is pi over 2. And similarly for U. So for example, if we have this green ray down here, what is the magnitude of this angle formed by the red ray and the green ray? We will get pi over 2. So this is what this theorem is telling us. The cross product is always at 90 degrees to both of the inputs of the cross product. So maybe let's write that down. U cross with V is always, let's say, perpendicular to, and let's say both U and V. Okay, that is something that you must remember. Okay. And let me just see how much time we have. We've got about 9 minutes. Maybe let us end here for today. So in our next lecture, we will take a look at an example discussing how to use the fact that the cross product is perpendicular to both of its inputs. Okay, so it appeared that everything went okay, that the setup was okay during load shedding. We did lose power, but thankfully it appeared that I did not lose connectivity, so that the stream just went on as usual. Okay, so let us end it here. What is today? Today is a Friday. I wish you all a lovely Friday. Oh, and remember, next week, Monday, there are no lectures, and next week, Tuesday, is a public holiday. So do take a look at the at ClickUp for the announcement regarding the tutorials. Next week, also no tutorials because we're missing Monday and Tuesday, and not everyone can attend the tutorials on Wednesday. If you're stuck with your homework, you can always ask on Discord. We will do our best to help you. Okay, and with that, I wish you all a lovely Friday. Goodbye.